Hello everyone. In this video, we are going to talk about chapter 13, section 13.1 through 13.3. So in this chapter, we're going to talk about forces and acceleration of kinetics of a particle. Really, what we are going to focus on is some free body diagrams and then Newton's second law, F equals ma. We're going to learn to write the equation of motion for accelerating body. We're going to learn to draw free body diagram and the kinetic diagram of for an accelerating body. So, starting with the Newton's three laws of motion. First law says a particle originally at rest or moving in a straight line at constant velocity will remain in this state if the resultant force acting on the particle is zero. Second law says if the resultant force on the particle is not zero, the particle experiences an acceleration in the same direction as the resultant force. And then this acceleration has a magnitude proportional to the resultant force. And then the third law says mutual forces of action and reaction between two particles that equal, opposite, and collinear. Now, focus on the second law. Okay, first and third law were used in developing the concepts of statics. Newton's second law forms the base of statics of study of dynamics. Mathematically, Newton's second law says F equals ma. F is the resultant unbalanced force acting on the particle, and a is the acceleration of the particle. The positive scalar m is the mass of the particle. Newton's second law cannot be used when the particle speed approaches the speed of light, or if the size of the particle is extremely small, so if it's in the size of a atom. And then if two particles or bodies have mutually attractive gravitational force acting between them, there's this Newton's gravitational force says F equals G times m1, m2 divided by r squared, where this F is the force between the attraction force between the two bodies. G is a universal constant. M1, M2 will be the masses of the bodies, and then r will be the distance between the center of the two bodies. And when near the surface of the Earth, the only gravitational force having any sizable magnitude is between the Earth and the body. So this force is called the weight of the body. It's important to understand the difference between the mass and the weight of the body. Mass is the absolute property of a body. It's independent of the gravitational field in which it's measured. So, in other words, if you say something, the mass of an object is 50 kilogram, it doesn't matter if I weighed it on the Earth or if I weighed it on the Moon, on the Jupiter, anywhere that you measure, the mass will always be the same. Okay, mass provides a measure of the resistance of the body to the changing velocity. And as defined by the Newton's second law of motion, m equals a force divided by acceleration. On the other hand, weight is not absolute. Weight totally depends on the gravitational field. When I say the weight is, let's say, however much Newton or however much pound, right? The weight changes on Earth. When you're on Earth, your weight is a number, and then on the Moon, on the Jupiter, on Mars, the weight becomes a different number. Okay, the weight is depends on the gravitational field, depends on where you are measuring the weight, and where g is the acceleration due to gravity. In the SI system, the unit's mass is a base unit and weight is a derived unit. Typically, mass is in kilogram, weight is calculated using this equation at W equals mg. And if the gravitational acceleration is specified to be in the unit of meters per second square, then the weight is expressed in Newton. So, in other words, Newton equals kilogram times meters per second square. Okay, and over here, that g, the value of g will be 9.81 meters per second square. In the FPS system, weight is the base unit. Mass is derived from weight. Weight comes first, and then we use weight to derive the mass. Weight is typically specified in pounds, and then the mass is calculated using this equation, m equals W over G, weight divided by G. And then over G, this G right here is in the unit of feet per second square, and then the mass is expressed in slugs. On the Earth's surface, this value of G is approximately 32.2 feet per second square. And mass in slugs, weight, that will be weight um, um, in pound divided by feet per second square. So slut equals pound second square divided by feet. Equation of motion here. So motions of particle is governed by the Newton's second law, relating to the unbalanced force on the particle to its acceleration. If more than one force acting on the particle, the equations of motion can be written as sigma F equals Fr, which the R stands for resultant force, equals ma. This is a vector sum of all the forces, and keep in mind forces are vectors, right? It's not algebraic addition, so it's a vector sum. To illustrate the equation, consider a particle act on two forces. First, draw the particle's free body diagram showing all the forces on the particle. And next, we're going to draw the kinetic diagram showing the inertial force ma acting on the same direction as the resultant force. So in other words, you have two diagrams here. First one is your F, right? Newton's second law says F equals ma. So you got two diagrams. Free body diagram shows all the F, and then the kinetic diagram will be the ma. So F equals ma. Okay. So this equation of motion is only valid if the acceleration is measured in a Newtonian or inertial frame of reference. For problems concerned with motions at or near the Earth's surface, we typically assume the inertial frame to be fixed to the Earth. We neglect any acceleration effect from the Earth rotation. For problems involving satellite, rocket ship, and the inertial frame of reference is often fixed to the stars. The equation of motion can be extended to include system of particles. This includes the motions of solid, liquid, or gas system. As in statics, there are internal forces and external forces acting on the system. What is the difference between them? Using the definition, let's imagine we have a bunch of little particles. So the total mass will be the little masses together as the total mass of all the particles in He as the acceleration of the center mass G of the particle. Then mg equals sigma of mi, ai, adding small particles together. The text shows the details, but the system particle sigma F equals mag, where sigma F is the sum of all the external forces acting on the entire system. Key points: Newton's second law is of nature, experimentally proven, not the result of any analytical proof. So mass is a property of an object, is measure of the resistance to a change in velocity of the object. Weight is a force depend on the local gravitational field. Calculating the weight of the object is an application of F equals ma, W equals mg. Okay, substitute that A acceleration with the G gravitational acceleration. That gives me the weight. Unbalanced forces cause the acceleration of objects. This condition is fundamental to all dynamic problems. So whenever you see problems involving procedures for application of equations of motion, we're going to select convenient in inertial coordinate system, rectangular, sometimes normal, tangential, or cylinder coordinates, depends on the problem. We're going to draw free body diagrams. That free body diagram is going to show all the external forces applied to the particle, resolve forces into appropriate components, and then later we're going to show the kinetic diagram. And keep in mind that when we say free body diagram shows all the forces, that will be all your F, and then the kinetic diagram will be your ma, right? F equals ma. And then resolve the vector into appropriate components. We're going to apply the equations of motion in the scalar component form and solve these equations for unknowns. It may be necessary to apply the proper kinetic relations to generate additional equations. Now let's take a look at two examples here. Example number one, we know there's this block that is moving to the right. When it's moved to the right, the spring is being stretched. What we're doing is we're going to draw the free body diagram and the kinetic diagram of the block when this S equals 0.4 meters. Okay, so free body diagram, we know that block, it's got a weight, right? Weight, normal force, weight coming down, normal force supporting it. And also in here, there's external force of 100 Newton supporting it to the right, pulling it to the right. And also, since the spring is being stretched, there is a spring force going the opposite direction, trying to put it back. Okay, so that's what this force is at the 3-4 angle. 3-4 defines how slant that angle is. Okay, so this will be the free body diagram showing all the forces applied to the block. And then your MA, right? These is all the forces, and over here is your MA. So mass times acceleration, and that's it. So we're not running any calculations. All we're doing is drawing some diagrams. Next example, we have this force being pushed the spring, right? We are looking, we know the spring constants and etc. We're going to need to draw the free body diagram and the kinetic diagram of the block. So what we have here, the weight coming down, normal force going up, and since we're pushing it to the right, this force is sort of pushing to the right. That means the spring is being compressed. That will be a spring trying to push back, right? So there's the spring force coming from the right to the left. And also there's a force pushing down 3, 4. Okay. So these will be the all the forces being applied to the block. And also these are all the F, right? And then the kinetic diagram will be your MA, mass times acceleration. Okay. This is all I want to show you in this section. Thank you for watching. I hope you find this video helpful.